in products, and our project name is automating battery welding. And I'm Calvin. Tim.
Alexis.
And I'm Chen. So Prodex is a manufacturing company located in Irvine, sponsored us computer engineering and the mechanical engineering team with the designing and implementing a semi-automatic system that will guide battery assembly through their welding machine, with an operator changing out the batteries after the welding process. Currently, they produce around 1,200 pieces with field technicians standing in front of their welding machine to load batteries and push buttons for operation in 1 week. What they expect is us and the mechanical engineering team can help them increase the production to 2,000 pieces in 1 week, and the system is easy and fast of replacement for technicians. So like I mentioned, this project is an interdisciplinary project by mechanical engineering and computer engineering. For mechanical engineering, they will create a semi-automated table, which we call carriage, drive parts through a welding station independently. But an operator will be used to interchange parts into fixtures. For us, we built another control system which interfaces between the semi-automated table and the welding machine they have. The system by us will also advance the assembly and actuate the welder horn when the next assembly is available. So our design goal is number one must be, actually this design goal is for both mechanical engineering team and us. So first is must be able to repeatedly weld 8 to 12 pieces, battery pieces assemblies. Number two, positioning tolerance between the batteries must be within 50,000 of an inch. Number three, easily serviceable. Number four, control backlash. Number five, support several different battery housing configurations. Number six, meets clean room requirements for a low particular room. Number seven, user interfaces, including LCD, push buttons, and rotary encoder. And last, number eight, noise control, efficiency and reliability, precision. Easy implementation, which means low cost and easy to assemble. So here is a short introduction for mechanical engineering team design. There are two main designs. First, when the start button is pressed, a synchronous operation will start, following the logic diagram on the left, which is the drive carriage towards the beginning. If it doesn't reach the end of the carriage, first battery position will be under weld horn. Then send weld horn a request to execute weld. Wait for completion, then advance carriage to next battery. Then if all batteries being welded, which counted by counter increasing, the carriage will stop execution. If not, it will keep sending weld horn signal to execute the weld. Second, at any point, if the emergency stop button is pressed, the current operation will stop. And here you can see some components the mechanical engineering team used, including the step motor, slide lead screw assembly, support rods, and the carriage. They are all made of aluminum. So while we are doing brainstorm for our control system, we come up a few different designs. Next, Tim will introduce you our first and second design.
So our first design was to use an RBOC PLC connected to a controller box where the user, with a GUI where the user can select the different battery types, weld times, hold times, the welding process. We wanted to create like an easy way without using anything external, but the problem that we had with this design was that there wasn't any external port connections on the welding machine that we can connect the PLC to. But there was a questionable method where we can open the machine and try to figure out a way to program the machine from the inside. But that would void the warranty that Prodex had with Branson, the manufacturing the machine. so we couldn't go that route. So we had to go to our second design. Our second design is pretty much resembles the first design in terms of functionality, but this time we would be using two external actuators to physically push the weld buttons on the machine. Instead of the PLC this time, we would be using two Arduinos in an I2C setup to send the weld selections to the actuators itself. This design actually would work for what we're trying to accomplish, but when we didn't like how the power consumption, as you can see, each linear actuator needed its own driver and NEMA 23 motors, which required too much voltage and a lot more torque power than we needed for the project. Despite all of that, we were still going to use this design, but when we presented the final design to Prodex, they didn't like how big and bulky it was, and it would take too much workspace around the welding machine. So we had to scrap this design and go with a third and final design, which Calvin will present to you.
So essentially, this third design, instead of using the big linear actuators, we're going to use Actutronics' L12i actuators. They come with an internal controller. So how we program the actuators is we're using the PTM, pulse width modulation. With the actuators, there's a pulse width modulation mode, which allows us to run it at a 5-volt, 1 hertz square wave. And with that, the duty cycle would basically control the amount of distance that the actuators will come out, would extend. With our design, we decided to come up with an 85% duty cycle for the actuators. So here's a brief test of the partial system of the ME's motor to the right and the actuators to the left. So the green button signifies the start. The limit switch. And then once the motor of the carriage is in position, it'll start moving the actuators. And then the red button to the right essentially is emergency stop. It'll stop both our systems. It'll lead the actuators back into its initial state and stop the motors, the ME's motor.
So in addition to the semi-automated system we created, we also decided to implement a safety system with using Connect, or like we like to call it the KISS. The reason we chose the Connect was because it was capable of displaying an RGB image. It had IR projector, a depth sensor, and it could formulate a registered image. The goal of the Connect was to replace the safety system button mechanic that was originally there. Originally, the machine safety system was to confirm that both buttons on either side were pressed before proceeding any welding. And if it senses that one button was not pressed any longer, it would stop the weld. Our system would stop all processes when a foreign object, whether it be an arm or a hand or any other unknown object, came into frame. Anything that could disrupt the machine and jeopardize someone's health, it would lead to the termination of our system's operation. In other words, the carriage would stop any movement and the linear actuators would reset back into their initial state. So to do this, we used the Open Connect library and the processing IDE and communicated data to an Arduino using a laptop serial port. By following some computer vision examples, we attempted to enclose the carriage in a 3D bounding box, and within that box, that box was within a larger environmental bounding box. Any major difference it detected would send a signal to the Arduino to stop all processes. So let's say that someone put their hand in the line of sight of the Connect. The processing application would send a signal to the Arduino, which is part of the I2C system, and that master would send a signal to the slave to stop the linear actuator.
So overall, our results ended up where our linear actuators actually was able to meld with the ME's carriage system. And we also were able to program the user interface so that we can control the different types of batteries of a rotor encoder. And there's also successfully implemented start and stop button. Unfortunately, we were unable to get the Connect to work with the ME's complete system. Unfortunately, due to time constraints, essentially we were unable to get the carriage to test with until 3 days ago. So our total budget given was $800. Unfortunately, due to the new micro linear actuators that we picked up, we went over budget by around $145.
For the tape?
Yeah, we'll do that. In the sound, then we'll still have the whole.
Oh, the demo, okay.
Yeah. So here's the video demo. You see that the carriage is going to the limit switch. And when it hits the limit switch, it'll move into the first position of the battery, and both our actuators will extend out to push the button on the motor. It'll keep on going until it reaches its max position on carriage.
And then for the Connect, since we couldn't put it together, we have a demo that just demonstrates that it would stop if it detects anything. And it's wait. So what we try to do is put a 3D bounding box around the actuator, and anything around it, if it detects any movement around it, it would stop. So since there's so many people, the ideal situation would be it's facing the wall, it's facing the machine, and there's nothing behind it. But since there's so many things moving right now, and it detects so much, it detected that it was an emergency, so it stopped the process. And we could start it up again if needed. But again, it would detect another emergency because of a lot of movement. So there's a demo that is working properly right here. And as we can see that it stopped, and then we could start it up again if needed.